So when I say the word alcohol, what pops into your head? Probably a drink, right? Well, in the world of organic chemistry, that's just scratching the surface. Alcohols are, wow, there's so much more. Think of them as these super fundamental building blocks. They're the essential tools in a chemist's toolkit, the things we use to build a whole universe of other molecules. So, in this explainer, we're going to really get our hands dirty and master that toolkit. We'll kick things off with the basics. What even are alcohols? Then, we're going to crack open the chemist's cookbook for 5 key recipes to make them. From there, we'll explore their two-sided reactivity, see how to transform them, and finally, learn to think like a synthetic strategist, ready to build anything. Okay, let's just jump right in. Before we can start using these tools, we gotta know what they are, right? So what is an alcohol, really? You know, it all boils down to one simple but seriously powerful little feature, the hydroxyl group, that classic OH. You can think of this as the active site, or the business end of the tool. This is the part of the molecule that does all the work. It's the reason alcohols do all the amazing things they do. Now, any good mechanic will tell you, you gotta keep your tools organized. Same thing in chemistry. We sort alcohols in 3 main ways. First, by how many OH groups they have. Second, and this one is a huge deal for predicting what's going to happen, is we look at the type of carbon the OH is hooked up to. If that carbon's attached to one other carbon, it's primary. 2 other carbons, secondary. 3, you guessed it, tertiary. And finally, we look at where it is relative to any double bonds. And look, this isn't just about being neat. This whole system is what lets us look at an alcohol and predict, with amazing accuracy, exactly how it's going to behave. It's a total game changer.
All right, so we know what they are, we know how to sort them, but where do they come from? How do we actually make them? Well, it's time to open up the Chemist Cookbook. We're going to check out 5 essential recipes.
First up is a real classic, substitution. We take something called an alkyl halide and just swap out the halogen for our OH group. But the way this swap happens is pretty cool. For a primary halide, the hydroxyl group comes in and attacks from the back, kicking the halogen out all in one go. For a tertiary one, it's a 2-step dance. The halogen leaves first, creating a carbocation, and then the hydroxyl group comes in. So on the surface, it looks like a simple swap, but underneath, there's some really elegant chemistry going on. Okay, recipe number 2. This time we're starting with an alkene, which has a carbon-carbon double bond. We add water across it with an acid catalyst. Now it follows something called Markovnikov's rule. Basically, the rich get richer. The carbon that already has more carbon buddies gets the OH group. But here's a little heads up, a pro tip if you will. This reaction goes through a carbocation intermediate, and those little guys can be, well, they can be shifty. Sometimes they rearrange themselves to become more stable, and suddenly you get a product you totally weren't expecting.
So what do you do when you absolutely need that OH group in a specific spot and you can't risk any of those pesky rearrangements? That's where recipe number 3 shines. Chemists have come up with these incredibly clever methods. You've got hydroboration oxidation, which actually puts the OH on the less crowded carbon. Then there's OMDM, which puts it on the more crowded carbon. The best part? Neither one of them allows for those annoying rearrangements. It's all about taking back control and putting that hydroxyl group exactly where you want it.
All right, another fantastic way to whip up an alcohol is by taking a carbonyl compound, that's something with a carbon-oxygen double bond, and reducing it. And just like in a workshop, picking the right tool for the job here is absolutely critical. For aldehydes and ketones, a gentler reducing agent like sodium borohydride or NABH4 works like a charm. But if you're trying to reduce something tougher like a carboxylic acid, you got to bring out the big guns, lithium aluminum hydride. We just call it LAH.
And for our final recipe, oh man, we've saved the best for last. This is the Grignard synthesis, and it is an absolute powerhouse. What makes it so special is that you're not just adding an OH group, you're also forming a new carbon-carbon bond. It's not just making an alcohol, it's building a whole new, bigger carbon skeleton at the same time. Seriously, it's like a master key for building molecules.
Okay, so our toolkit is stocked. We can make pretty much any alcohol we want. Now for the really fun part. What can we actually do with them? Let's see them in action. Turns out, alcohols kind of have 2 different chemical personalities. And you know what's wild? It all comes down to a super simple choice. The entire reactivity, its whole chemical personality, boils down to one question. Are we going to break the bond between the oxygen and the hydrogen, or the bond between the carbon and the oxygen? Each choice sends the molecule down a totally different reaction path.
So, let's look at path number 1, breaking that OH bond.
When that happens, the alcohol is acting like a weak acid, but they're not all created equal. Now take a look at the diagram here. See those alkyl groups, the CH3s? Think of them as little bullies, constantly pushing their electron density toward that oxygen atom. The more of those groups you have, the more crowded with electrons that oxygen gets, which makes it harder for it to let go of its hydrogen. That's exactly why primary alcohols are more acidic than tertiary ones. It's just such a perfect example of how the shape and structure of a molecule completely dictates what it can do.
Okay, so we've got these two paths an alcohol can take. Now let's see how we can exploit that, how we can put these tools to work and do some really cool transformations. This is where we start converting simple alcohols into all sorts of other useful stuff.
All right, time for a little thought experiment. Imagine you're in the lab. A professor walks over and hands you 3 unlabeled test tubes. You're told one is primary, one's secondary, and one's tertiary. So how do you figure out which is which just by using their chemistry?
Well, the answer is a classic little trick called the Lucas test. It's designed to see how fast that CO bond breaks. You add the Lucas reagent, and if the solution turns cloudy, like instantly, boom, that's your tertiary alcohol. That cloudiness, by the way, we call it turbidity. If it takes a few minutes to get cloudy, you're looking at the secondary. And the primary one? It'll just sit there at room temperature doing absolutely nothing. It's a fantastic, quick visual test.
But this reactivity isn't just for telling things apart. We can harness it to do some major molecular surgery. So look on the left. That's dehydration. We basically rip out a water molecule using acid and heat, and bam, you've made an alkene. Now look at the right. This is oxidation. And this is where things get really, really cool and specific. We can turn a primary alcohol into an aldehyde or a secondary one into a ketone. The tertiary one, it doesn't react at all. It's incredible how we can go in 2 completely different directions from the same starting material.
And this idea of control with oxidation is so important, we have to look closer. With a primary alcohol, if you use a mild oxidizing agent, you stop at the aldehyde. But if you hit it with something strong, you go all the way to a carboxylic acid. Secondary alcohols will only ever go to a ketone, and tertiary ones just stubbornly refuse to oxidize. This is what being a chemist is all about. It's strategy. You're picking the right tool for the job to get the exact molecule you're trying to build. Wow. Okay, we have covered a ton of ground. We know what alcohols are, how to make them, how they react. So now it's time to put it all together. Let's start thinking like a synthetic strategist.
This chart right here, this is basically the ultimate cheat sheet. This is how you start to think like a real synthetic chemist. So let's say your goal is to make an aldehyde. You just look at the chart. Okay, I need to start with a primary alcohol, and I need a mild oxidizer like PCC. Done. Want to make an alkene? Just grab almost any alcohol, add some acid and heat, and you're good to go. This is how chemists work backwards from the goal to figure out the perfect plan.
You know, when you peel back all the layers, all the different reactions, the recipes, the tests, it all comes down to just 2 fundamental ideas. If you get a feel for carbocation stability and you can see where the electrons are hanging out in a bond, its polarity, you've basically cracked the code. You can predict what's going to happen in almost any of these reactions.
So there you have it. You've got the cookbook, you've got the tools, you've got the strategic cheat sheet, you understand the fundamental rules of the game. So the only question left to ask is, with this amazing toolkit at your fingertips, what are you going to build first?